So friends, let's here examine the concept of free energy in thermodynamics. Free energy by definition is the part of the energy contained in the system which is available for doing thermodynamic work. Here the monkey is opening the coconut and the energy requirement is met with the metabolic processes happening inside his body, and the whole energy made available in his body due to the metabolic process are not directly available for this process or this work, because a large part of energy is used for his physiological activities and for other activities like jumping from here and there, etc., etc. And for doing this kind of useful work, only a part of the total energy produced inside is available, and that part of energy which is available for this kind of useful work is called free energy. And for a system, thermodynamically there are two kinds of free energy. The Helmholtz free energy, which is represented by the letter A, and this is defined for constant volume processes. And the second one, Gibbs free energy, is valid for constant pressure conditions. And we know that constant pressure condition is more relevant for a chemical laboratory or for chemical reactions. Therefore, Gibbs free energy is more relevant for chemical reactions in laboratories than Helmholtz free energy. And in the following we will see the significance and physical meaning of the two and the difference between the Helmholtz and Gibbs free energy, etc. And before that, let's see where do the two free energy concepts, the Helmholtz and Gibbs free energy concepts, arise from. Actually, they come from a relation called Clausius inequality, which is based on the definition of entropy in terms of a reversible heat. The amount of work done in a reversible process is larger than the work done in irreversible process. And as internal energy is a state function, the change in internal energy during a process will be the same whether it occurs in a reversible pathway or in an irreversible pathway. So writing down the internal energy equation in terms of work and heat according to the first law of thermodynamics, we can write the sum of the heat and work in a reversible process equals the sum of heat and work in irreversible process based on the internal energy criterion. Rearranging this, we achieve this expression. By taking the first part of this equation, we can write then the reversible heat is greater than or equal to the irreversible heat. And this implies that the reversible heat with respect to temperature is greater than or equal to the irreversible heat with respect to temperature, and the reversible heat with respect to temperature is by definition the entropy change occurring in the process. Therefore, we have this expression, that is change in entropy is greater than or equal to the irreversible heat with respect to temperature. And this expression is called Clausius inequality. It looks very simple, the expression, but Clausius inequality has got very crucial importance in following discussions, especially in the context of defining free energy. Now we will see how this relation Clausius inequality leads to the formulation of two free energy concepts, Helmholtz and Gibbs free energy. So to achieve that, let's impose two conditions, the constant volume conditions and constant pressure conditions separately. So looking at a system, a heating process at constant volume, we know that in the absence of non-expansion work, the work is then the expansion work which is given in terms of volume change. As we have got the constant volume condition, that pressure volume work will be zero, that is the work is zero. And this leads to the first law expression that the heat at constant volume equals internal energy. And from the Clausius inequality, we can rearrange this to get this expression, that is ds minus dq by t is greater than or equal to 0. Here now we are going to replace this dq in terms of the internal energy as we have done first. So we have this relation. After rearranging this, we get TdS is greater than or equal to du. And at constant internal energy condition, we can say that the TdS is greater than or equal to 0 at constant volume and internal energy. And likewise at constant entropy condition, the change in internal energy at constant volume and entropy is less than or equal to 0. And this is our source relation, that is TdS is greater than or equal to du at constant volume, which we require for later while defining the Helmholtz free energy. Before that, let's see the constant pressure condition. Here we know at constant pressure, the heat at constant pressure is equated to enthalpy by definition. So from Clausius inequality, after rearranging and replacing the heat term at constant pressure by enthalpy, we get here, and rearranging this expression, we are reaching this expression that TdS is greater than or equal to dH. And this is an important formulation of Clausius inequality at constant pressure condition. And imposing the condition of constant enthalpy, the dH value is 0. Therefore, we can write the change in entropy during a constant pressure and constant enthalpy process is always greater than or equal to 0. And likewise, imposing the constant entropy condition, we reach that the change in enthalpy during a constant pressure, constant entropy process is always less than or equal to 0. And this expression, the formulation of Clausius inequality at constant pressure condition, is giving rise to Gibbs free energy. So we have these two expressions, TdS is greater than or equal to du and TdS is greater than or equal to dH. The first equation valid for constant volume and the second one for constant pressure. And the first equation give rise to the formulation that du minus TdS is less than or equal to 0, and rearranging the second one we get a similar expression in terms of dH, the change in enthalpy. And these two terms give rise to expression U minus Ts, that is equated to A, the Helmholtz free energy, and the second one gives H minus Ts, that is equated to G, the Gibbs free energy. And these two are the free energy functions A and G. A, the Helmholtz free energy, G, the Gibbs free energy. They are helping us to define spontaneous processes with better clarity than entropy and energy can themselves do. Let's see how it works. So change in Helmholtz free energy during a process by definition is du minus TdS, and based on the Clausius inequality for spontaneous process we get this expression, and likewise we get the expression in terms of Gibbs free energy. And these two expressions define spontaneous processes, and this expression that is equated to 0 gives the condition for equilibrium processes. That means for a spontaneous process, the change in Helmholtz free energy at constant volume condition and change in Gibbs free energy at constant pressure condition are always less than or equal to 0. And exclusively for equilibrium condition, the change in Helmholtz free energy and change in Gibbs free energy are equated to 0. And this is important consequence of Clausius inequality. And let's now see the physical meanings of Helmholtz and Gibbs free energies separately. So coming to the Helmholtz free energy, we have seen that for spontaneous process, this is the condition in terms of Helmholtz free energy. That means the system moves spontaneously to a direction of lower Helmholtz free energy A. And A, the Helmholtz free energy, indicates the maximum work that can be obtained from a system at constant temperature. And let's now see how it comes out. We have from the Clausius inequality this relation, and the first law of thermodynamics, if you want to replace this dq term by using the TdS shown here, the equality will be replaced by this sign. And hence by rearranging we can write the work associated in a process at constant temperature and constant volume will be greater than or equal to the internal energy change minus TdS term. And from this relation here, the maximum work occurs if the work dW equals du minus TdS. So for maximum work we can write the expression in terms of equality, and du minus TdS is obviously the dA, which is the change in Helmholtz energy of the process. So the maximum work obtained from the system is the change in Helmholtz free energy during the process. As I said before, Gibbs free energy is the more relevant term in a laboratory condition because there we are dealing at constant temperature and constant pressure conditions than the constant volume condition. As we have seen before, the change in free energy should be less than or equal to 0 for a spontaneous process in general, and exclusively for an equilibrium process, the change in Gibbs free energy should be 0. And this idea of Gibbs free energy is used in chemical processes like fuel cells, etc. And spontaneous processes occur in the direction of lower G. That means when a system undergoes a spontaneous process, its free energy should change from high value to low value. And based on this idea, based on the Gibbs free energy concept, we can explain the spontaneous endothermic processes more clearly than we do with the help of entropy or energy considerations. We have the Gibbs free energy by definition like this, and for an endothermic process we know the enthalpy change is positive. Therefore, in order to have the dg to be negative, that is to be less than 0, this equation says that the TdS term should overweigh the dH term. That means the entropy, the ds term has a strong contribution to the process, or the process occur at the expense of entropy. So during an endothermic process, there is a decrease in entropy. For example, when liquid water melts to form solid ice, we see that there is a decrease in entropy, more order is achieved, but this entropy decrease occurring to the system is balanced by the entropy increase occurring to the surroundings, because the heat lost by the system was taken by the surroundings. And Gibbs free energy implies the maximum additional work that the system can perform at constant temperature and pressure. Let's see what does this maximum additional work means. The change in free energy during a process can be given like this, and we can replace this enthalpy. By definition, it is internal energy plus pressure volume term, and by expanding this brackets, and then we can replace internal energy in terms of heat and work, and the equation grows in terms of heat and work. And now we know that maximum work is obtained in a reversible process. So the maximum work condition is the reversible process condition. So here is the reversible work and reversible heat. And imposing the constant temperature and pressure condition, the Gp and dt terms from this equation disappear. Likewise, the TdS, which is replacing dq, and the minus TdS get cancelled, and in the end what we have is dg equals dw, the reversible work, plus the pdv term. And we know the reversible work, the work include both expansion work and non-expansion work. So at the reversible condition, I just split this work into the expansion work and the additional work or non-expansion work, and the expansion work is minus pdv by definition, and therefore dg can be equated to the maximum additional work or maximum non-expansion work, and therefore the change in free energy during a process gives the maximum additional work that the system can perform at constant temperature and pressure conditions. So the monkey we have seen in the beginning, he is using his Gibbs energy available in his body, in his system, to open up the coconut. That is, to do this additional work. And the net difference in free energy before and after performing this work will give you the maximum amount of work. Let's now see how the Gibbs-Helmholtz equation explains the variation of Gibbs free energy with temperature. By definition, here is free energy, and entropy can be defined like this. And from a fundamental relation, we have this expression, that is, the change in free energy with respect to temperature at constant pressure is negative of entropy. And the negative of entropy, I take it in this form from the first equation over there. And if you want to talk about equilibrium conditions, temperature is a very important factor over there, because temperature influences the equilibrium, and the equilibrium is governed by free energy such that the change in free energy is 0, or the free energy on both sides of the equilibrium are the same. So at equilibrium, we talk more about the G by T term than G. So we look for the derivative of G by T with respect to temperature. So by performing the mathematical operation, the derivative operation, we reach at this expression. And here I am replacing this dou G by dou T term ready-made from here. So I have this, and by solving this I get this expression, that is dou by dou T of G by T at constant pressure is minus H by T square. There is variation of g by t with respect to temperature. At constant pressure is given by minus h by t square, that is in terms of enthalpy of the system. And this expression is called Gibbs-Helmholtz equation. This is very important equation which helps us to understand the equilibrium processes, equilibrium chemical reactions in terms of free energy and enthalpy. And that's all about Gibbs and Helmholtz free energy functions for the time being. And let's see the thermodynamics of mixtures in the upcoming session. We will be focusing on partial molar properties. Thank you.